right, let's get going. And that was George. He struck two. So the clocks will go off here and within a couple minutes of each other. And we're living with clocks in here, so that's what we're gonna do. I've had people say with their clocks, is there any way you can make it tick quieter? Is there any volume control on it? Well, the quartz movements have volume controls, some of them. But no, I would say, and some people just will not have a clock in the room at all. You run into all these issues with people about their clocks, yeah. Well, welcome to this clock talk, and thanks for coming. And what about this library? Isn't this beautiful? You know, and it's great. I do want to say thanks to Kevin, who's helped me set this all up so much. That's Kevin back there, he's the library guy. And my wife's cousin, Tom Riddle, who will do all the video stuff for us, of which we have some, kind of near the end of what I'm talking. Hi, come in, have a seat. You should be getting a handout somewhere. Yeah, you need 3 sheets of paper. And my grandson, Tristan, who I've kind of trained through the couple years here in clock stuff, and he and I are going to do some work on this one right here tonight. Try to save your life from doing something stupid, like take a clock apart without getting rid of the spring power first. And which I did as a kid. All right, but this library is so beautiful, and I'm so happy to be here because I knew Grant in Alberta, Carlin, taught with Carlin for many years, and Grant was a great guy, just a wonderful man. And he sat on the board of this library, and that's why it looks like the old building. That's what I was told. That Grant was the one that made sure that it looked like the old building. And here it is. Okay, I'm Richard Whitmore. Most folks call me Dick these days. Some call me Mr. Whitmore still. And 5 call me Dad. 24 call me Papa or Mom. And 23 don't call me anything yet, except one little guy. He calls you Papa. So we have 23 great grands, and still working on it. Well, why did you come here? I'll bet all of you guys own some clocks. And you're wondering about your clocks. Kevin told me that some people were saying, can I bring my clock along with me? Did you bring your clock? All right. I won't fix any clocks for anybody here tonight. I might be able to tell you a little bit about it in some way, but won't fix any except we won't fix any. We'll make sure this thing won't blow up in your face. The reason I'm here is because you're here. And so in doing this clock repair stuff, I found out something, it surprised me. I greatly expanded and was very interested in not only just the clocks, but time and how we got here with our timekeeping and so forth. There's a whole bunch of history behind clocks, particularly with John Harrison. On your sheets that I've given you, there are 17 clocks listed. All of the things in here are clocks, including number 14. You look on your sheet, they're not in order in the room. So if you look down to number 14, you'll see that that's the annual calendar. It indeed is a clock. And then also we have the globe. number 15. And it's a clock. And you'll learn why here tonight. After we're done, a little after 3 probably, I have to leave at 3:40. I have to go home. My family's having a birthday celebration for me. Today is not my birthday, it was last week, but they're doing it today. So a lot of things going on, big family, and so 4 o'clock on Saturday, the 9th, was the only time we could fit that in. And so, some of you may want to hang around a little bit after 3. Kevin said he was going to be here till 4, but I'm going to leave at 3:40. But the clocks are going to be here. I may take my toolboxes with me, but the clocks will be here in case you want to read about them from what I've given you, or maybe take some photographs. I don't know. You're welcome to do that. I just asked you don't touch them. Okay, now when you look at your clocks at home, or for that matter any clock, you see the outside. Clockmakers see the inside. And so today what we're going to do is talk about the insides, basically. A lot of people think it's the look of the clock that's the big deal. And in some cases that's true depending on the clockmaker. But today we're interested in what's going on inside. All right. All clocks, any timepiece. This word clock came down to us from Old English. It had an E on it originally. And in Old English it meant bell. And so, to use the word clock, we think about something hangs on the wall, sits on the floor, goes in the shelf, sits by your bed, in your car, and watches, that's the things we wear. But essentially they're the same thing. And so they have some elementary parts, 3 of them. They are power, regulation, and display. That makes a timepiece. All of the things I talked about, all 17 of those things on your list have those 3 parts, including the calendar, including the earth. All of those things have the same thing, including, where did sandglass go? There he is, okay. Okay, they have 3 parts. All right, let's talk about power a little bit. In a timepiece today, we have 3 kinds of power. We have weight, we have spring, or we have electric. Very few models of clocks may combine those, but usually not. Usually it's all run by weights, or it's all run by winding up a spring, or it's all run by electric. The electric can be different things, and we'll talk about that in a moment. Regulation. If it's regulated, well, let's do power first, because we want to do our thing here. I want to do that thing. Okay, so with the power, we have gravity. The reason weights work on a clock, because of gravity. So gravity is kind of a free piece of power laying around, and all we got to do is harness it somehow. So we hook a weight on a cable or a chain, hoist it up to the clock movement, and it tries to go back down. And that'll make the clock movement run. It's really pretty handy. Is gravity the same all over the earth? No. Is it much different? No. But it is different in different places of the earth. So this Silas Willard over here, that's this guy. We call him George. We've always called this clock George because it's got the reverse painting of the George here. it's not done very well. We think it was touched up at one time, and so George kind of looks like he's got a black eye. But this is a pendulum-driven clock, and it is a pendulum regulated clock, and it is weight driven. There's two weights hanging here, one for the strike, one for the time. Cable goes up, goes across the top, goes down to the main wheel, it's wound up. Originally it was done with catgut, which is the intestines of a pig. Today we use nylon in place of catgut. You never would use, on this clock, you would never use steel wire or brass wire or cable, because it would cut the little wooden whirler loose. And on lots of clocks, in fact, almost all of these, you've got to be really careful what you're doing to them if you want to preserve the antiquity of it. And when you get into the movement where nobody sees it, you kind of like are having to follow the rules of, well, be honest here, you know, am I going to keep that screw or throw it away and get a brand new screw? So you run into that. Or we have, as I said, for power, we have spring. Now Tristan and I are going to do something here, and I'm going to stop in my little talk here about all of this and do something, because I think it's so important. And I have here in my notes, caution, disassembly of a clock movement never should be done until the spring power is completely released. Why?
It's going to spring up and hit you in the face.
Oh, yes. Eye problems, face cuts, cuts all over your hands, just awful. Now, I took a Big Ben. No, it was a Big Ben? Yeah, it was. It was one of these black alarm clocks my folks had for years. Wind it up every night. Well, when that baby stopped, I got it. And you know what I did? Of course, I took it apart with the spring wound up. And it will go. I mean, it'll just, and away it goes. Well, Tristan and I are going to make this one be safe. It's wound up, and it's a time and strike movement. That means it has two mainsprings in it. And there's the one that's striking, and it's trying to do its thing right now. And I'll wait for that to stop, because when you bump the levers, it takes off. But each system, the striking system and the timekeeping system, have a mainspring all wound up nice and tight. There it is. Now we need to take the power off. So we do a little trick here. This is typical A1, first course clock repair. How to let the power down on a spring-loaded clock. Need a tool, and so what we got here is these different, the winding arbors on clocks are squares, and they come in different sizes. Number 00 on up through number 14. So real fat to real tiny. This is a 6. So we have a 6 bit in this handle. That'll fit right over the square. We've got a whole bunch of them here, so that's something you would have to buy. One to set up like this with a handle. And when the clock is wound up, there's a little latch in there. It goes click, 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 click. If you have a clock at home that's a wind-up one, you go like this, and it goes click, 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 click. What you're hearing is a little lever going back and forth on a cog tooth. And it's, every time it clicks, the little lever goes down into between two teeth and keeps it from unwinding. So what we have to do is release the pressure on the lever, and at the same time pull the lever back, and then Tristan very carefully will release his grip on that tool and allow it to rotate in his hand, and the clock spring will expand and will be safe. Okay? I'm going to be the bench voice. I'm going to hold on. Tristan's doing the work, because if it goes, he gets it. So he's doing the time side first. Pulls back the lever, releases it, lets it unwind.
we can't see them, so we're depending on your description here.
Yeah, well, I'm gonna pass it around here in a minute.
One of them.
Which one's good, be pretty big here. That's good. Okay, now we got that side done. This one is kind of buried back behind another part, and so he's gonna have to get down in there to get a hold of the lever. See how close his face is to it? Oh, I think, Diane, that would get him the road. I know Dr. Curtis does that, but. Okay, there we have it. We're gonna send this around to you, pass it around, and you can yeah, John, you can come and get this, so we can start it out. And I want you to notice something. The bigger wheels, there's one here, a big wheel, and there's one here. I'm saying wheel. Why am I not saying gear? Because clock people talk about wheels, not gears, for a reason, not just to be funny, but there's a reason. I don't want to explain that to you, but that's why I call them wheels. The big one is the one the power goes on. And as it goes on up the train, strike side, time side, they're independent of each other. The wheels will get smaller. The big wheel always drives the pinion, which is the small part on the shaft with all the wheels. And so when you get up to the top, as you will see in a thing we're gonna do here in a little while, that there's a tremendous amount of transfer ratio as it goes up. The big wheel will turn very slowly, although it's got a lot of power on it. The next wheel up will go much faster. And then that one is driving a pinion and it has a big wheel on it as well. Come in, please. Come and sit. And get a handout on the table there. And so it goes faster and faster until you get up to the time. I'm going to turn the big wheel and watch this part right here. Can you see it? Watch. I'm turning it just a tiny bit, and that thing is really flipping around.
I'm gonna need that.
I would not attempt to take my little finger and put it in that big wheel and try to stop it. It would cut my finger off. But I wouldn't be afraid to stick my finger in that thing and hold it. So there's that much loss of power going up to the top of the movement. All right, John. Okay. Okay, so that's a safety thing I wanted to get out of the way right away. Spring wound clocks are dangerous. Okay. Weight driven clocks are too, depending on the weight. We'll be talking about the old courthouse here. We're gonna be talking about the clock that was in the courthouse. And you have a picture of it right now. The weights on that, are 400 pounds each. 400 pounds each. Here's the weight that George has.
You know what I'm saying?
Yes. Yeah.
This is about 10 pounds.
Work a half hour.
I don't know if you see it. You see it?
If it's set up to do that.
So, yes, weights can be dangerous, especially in tower clocks. If they get loose, they'll go through the floors, ceilings, all the way down. There is a very famous weight-driven clock in the world. I'll bet you know what it is. It's a tower clock, by the way. That's a hint. Big Ben. Okay, that's a nickname. Big Ben is a nickname for that clock in the Parliament building, Parliament it's called the Westminster Parliament Building. And so the tune that we hear very familiarly being played by some of these clocks, the chime tune that goes bum, 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 that's the Westminster chime. Here's the story. In the early 1700s, George Frederick Handel, a German musician, wrote the Messiah. Anybody heard the Messiah? Know about the Messiah? Okay, it is a oratorio, which is a 2-hour presentation, all Bible verses, all talking about the Messiah, and all set to music. It's opera-like. It was very popular. Well, there's no other words in it except Scripture. And so right in the middle of the thing, there is a part out of the book about the book of Job, from the book of Job. And it's called, I Know That My Redeemer Liveth.
Very confusing.
And there is, leading up to the actual
I
song,
don't really know, but I would just
there's
estimate it's
3 bars of music that have 4 notes in it.
maybe older, maybe
Bum, 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 whatever those are, and they mix them all up. Well, the same thing happens with these chiming clocks. Why? Because the music was so popular that tower clock makers of the day began to want to put bells in their towers that were playing those 4 notes. And then, when they went to make the one in London, they did it. They did those 4 notes. And the bell tone, the bells, each of the tone bells weigh 50 tons each. The strike bell in that clock in London weighs 100 tons. And it was made on site. All right, so I'm telling you all this because it broke. They had it's way up in the tower. You can take elevators and go up and sit there and church view things like, and watch the clock run and all of that. It was open to the public.
This is the front.
Well, they heard this big boom and crash, and they thought somebody might have put a bomb up there. Well, they did all right. A part failed, and when the weight started to descend, powering the strike, the part that was supposed to stop it broke. And it kept going. And this huge amount of weight, which was 1,500 pounds, started down. Fortunately, what happened is what used to happen on our reel-driven fishing tackle. Remember those buggers that had a reel and not a little, if you didn't keep your thumb on it just right, it backlashed and knotted up. Well, that's what happened. And the cable tangled all up and stopped it. But by stopping it so quickly, the parts of the clock exploded, went all over that room. The winding arbor, we have this one here. See this winding arbor? See this cable? Right there? This is from the strike side of this clock. Well, this part in Big Bend weighs 1,500 pounds. Just the arbor. In the Seth Thomas, you have a picture of that was in the tower of the courthouse here in Ravenna. It weighs 250 pounds.
No, I thought you'd be more
She's
confused.
No. I never see that.
All right, so other kinds of power then. All right, so the other kinds of power here we got. Okay. We talked about spring power. Okay, I want to get into electric power now. That's very interesting. And when we get into regulation, I'll talk more about it. But the electrical part is what? Batteries and alternating current. And there wasn't a time here in this country, in the world, when alternating current was the way to go. Because that made clocks really be accurate. And there's a reason for that. Okay. And then, of course, batteries. Where's clock 13?
Behind you.
Behind me. Okay. This is a cute little thing, right? It's a little choo-choo train. And it has this was a gift. I never would have bought this clock. The movement was quartz. It failed. I replaced it, and now the only thing it does is keep time. But it used to do other little tricks, like go boop, boop, and the train would go around, and that sort of thing. Well, that's failed. So I've got this little black box back here that you've seen with your clocks. You put batteries in them, right? And you know how we fix these?
Yeah.
K is white, right. Now, you get it out, get a new one. I've got them. I'll put them in for you. I'll charge you to do that. But you can go to Walmart and get some of this stuff. Or maybe you just go to Walmart and buy a whole new clock and just toss the whole thing. That's how we fix them. We don't take quartz movements apart. Okay, so that's the other part of the electric. All right, now regulation is very interesting because that's where we begin to take this power and put it out in regular intervals. So we have this huge amount of power inside a clock, but we don't want all that power to go at once. We want to meter it out in little bursts of power because we're doing a timing thing. This is a timekeeper. And so that's why we're doing that. That's what George does here. That's what the cuckoo clock's doing. Whoop, George stopped. Why'd you stop, George? Oh, because it took the weight off. And that's what stopped it. So it's 227. Okay. And so every time this ticks, get my amplifier out, will you? In the black wire with the clip on it. Every time it ticks, that's a portion of time for this clock. That's not 1 second. Some clocks do tick every second. Big grandfather clocks that have 114 centimeter pendulums on them, they tick once each second, 3,600 times an hour. Where are you? Standing line. Yeah, I'm gonna let you hear it tick. I never thought I could do that. That's faster than 1 second.
Off a little bit.
Yeah. It is, it beats a little off, yeah. Okay. Okay, Diane, I lost my sheet. What did I do with it?
Oh, here it is.
Oh, yeah. Thanks. Okay. So how to control this duration of power that this clock spits out? Inside the mechanical clocks, there is a part called the escape wheel. The escape wheel, every time the clock ticks, the escape wheel stops and restarts. That means the entire train of wheels starts and stops every time it ticks. It's like that. The escape wheel has bent teeth in it. You saw it when we passed them around. It has bent teeth in it. That bend is there for a reason. Because the part that keeps it from getting away, escaping, that is hooked to the pendulum, goes back and forth, catches the tooth. Goes on one side, catches it, the tooth smacks into it, that's the tick you hear. Rocks back the other way, it lets that tooth go, but catches the other tooth. It ticks. That's the ticking you hear in the clock. The distance between the points of the teeth and the length of time it takes that escape wheel to go from one tooth to the other is very critical. It's adjustable. At the bottom of the pendulum, did George close his own door? No, I closed it. Tristan closed it. There's a little nut down here. See it? All pendulum clocks have this ability to adjust the length of the pendulum. The longer the pendulum, the slower the clock will run. The shorter the pendulum, the faster the clock will run. And so that's adjustable. So if your clock is gaining or losing time and it's a pendulum clock, you can turn that nut and shorten the pendulum or unscrew it and lengthen the pendulum. And it doesn't take much to make it change, say, 2 minutes a week. It really doesn't take much. All right. So, each tick, right? Balance wheels. We're gonna pass this clock around. And I'm gonna have Kristen to do it. This weighs 19 pounds. It's all made of, I made it. It's all made of brass, made 6 of them. One year for all my kids, and this one too. And what we're gonna do is put it on your table, and you can slide it back and forth and then change it to the next table. And what you wanna see in there, look, turn it to the back side, Tristan, so they can see the balance wheel. At the top of that movement is a balance wheel. A balance wheel simply amounts to a wheel with a hairspring wound up in it. And it will go all the way in one direction, flip a little latch, and go all the way back in the other direction, and flip a little latch. This one runs at 9,000 an hour. Would you put the meter on that one?
You want to?
Yeah, just leave it sit there, put the meter on. We'll hear it going. Balance wheels are great. They're not as accurate as pendulums, though. However, there's an advantage. We picked that clock up, moved it over there. If we picked George up and moved him over there, he would have stopped, because a pendulum can't stand much wiggling around. And so any of your pendulum clocks have to have stability. Your grandfather clocks that sit on the floor, if the floor is rocking and rolling a little bit, or the carpet's too thick, it may stop because it can't stand that kind of movement on it and keep going. But balance wheels aren't like that. It's too close. Faster tick, right? 9,000. That's 9,000. So see, the balance wheel is going very fast. Just like that. And if you can see the spring in there, John, and, you know, you can see the spring inside expanding and retracting as it's going. So that's balance wheel. And so that's another way of regulating. So this kind of clock's pretty good. It can stand movement. Our mechanical watches that none of us wear anymore, except for special occasions, or maybe you have a pocket watch of some kind at home that still works a little bit. And when you wind it up, you can hear it in there going, and that is a balance wheel. Why? Well, pendulum wouldn't work in that. And so they do a balance wheel technology. And
Try to make it clear,
and
They
so
actually made one
that
just
worked great. Now, when you go looking around at things here, one of the things you need to see is that number 1, which is over here with John Harrison's stuff. Right here. Because that's where a man spent
And
a whole, and the details are in your handout for number
How do
one.
you slow it down?
He's the one that invented the clock
This,
Yeah.
that would be
you can
so
actually
accurate
adjust that
that
spring
it
on the
could
side.
be used
You can
to
adjust the tension
locate
on
your
the spring.
distance
So
from a
it'll go faster.
faraway port, aboard ship when you're in the middle of the
Usually
ocean.
also, if
With the
you
second.
And that's John Harrison, and he was able to do that. That was a huge problem in that day. You can Google that, Google John Harrison and read what it says about that. Or you can go to the library here and get some reading material
But I don't know.
about John Harrison.
but I like that it's
Okay. So, small little increments of time is what we're trying to have happen, but they have to be the same length. They can't be hit or miss. It can't go tick, 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 it has to go tick, 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 like that, and it's adjustable, in a clock. So, balance wheels and pendulums.
Oh, I'm actually looking at that.
Every time it ticks, the escape wheel moves one tooth. Okay. John Harrison devised, what he was good at was figuring out metallurgy. He made the springs work. And so he could do a balance wheel, because aboard ship, you have a grandfather clock work. It just rocks and rolls too much. But, so that's why he did that. All right, let's talk about this alternating current. Here's some fun here. If I say to you, Elon Musk, what do you say back?
Tesla.
Tesla. Okay, and so, at the end of the 1800s, we wanted to electrify our communities.
Even when tilted,
The big person in electricity of that day
which is great for ships.
was Thomas Edison. And Thomas Edison wanted things to be direct current. He thought that was the best way to do it. Direct current is what comes out of batteries. You can take a hold of your batteries, you do. You hold them by the ends. There's a minus charge in one end and a plus charge in the other, but you don't get electrocuted. You don't get shocked. It's low voltage. Volt and a
Yeah,
half
back and
or
forth.
maybe 3 volts.
And we call it when the spring
But-
grows, the strings call it breathing.
You can't get hurt by it. So he thought it was safer. He was right. But there is another kind of, the problem is, with direct current, you can't send it across wires very far. It loses its amperage. It loses its power. But you can do it with alternating current. You can send from a long distance, you can send a little shot of it. Boop, boop. You send it like that, and it doesn't lose that
And you can
power.
see, if you like turn on the side.
It's called alternating current. Well, here comes Niagara Falls.
Because for ships.
And he said, you know, we have this falling water, and we can build these dynamos that this free falling water power will spin. And the question was, how fast do you want them to spin? Well, we can do anything. We'll make them go 100, we'll make them go 50, whatever you guys want. They didn't know which one to do. The clock people of the day came along and said, make it be 60. And they had an automatic regulated power coming out of the wall socket, 60 cycle. So, remember those electric clocks that we used to have that hanging on our kitchen ceilings that had a little plug behind them that you could plug them in? They kept pretty good time. They really did. Because coming out of the socket was 60 cycle, because the dynamo off of Niagara Falls or wherever was going 60 times a second, 3,600 times a minute. And it was an automatic regulator. Didn't need a escape wheel, you needed none of that stuff. Just plug it in, and it was great time. It was fine. So the people that wanted all that to happen, that wanted to use alternating current, were Tesla and Westinghouse. Those were the two big names. And so why did Elon Musk choose Tesla for the name of his automobile? Because of the history that we have with Tesla, the man behind alternating current. So we have that kind of power. But this is kind of out of phase now. There aren't many electric clocks. I can still fix those, kind of. Can't always get all the electric motors like we used to. But some of them we can fix. And they work fine. Okay. Now, in this range of regulators, if you took a grandfather clock and got it started in January 1, never touched it except for winding up the weights, how far off would it be on December 31 of that year? Well, it may have gained, who knows how much, or lost. You know, so you'd regulate it, you would work on that. You try to get it so it wouldn't, you know, only once a week would you advance it 1 minute. You know, that kind of accuracy. Well, they needed better accuracy. So they had pendulum-driven clocks with weights that ran the clockwork that drove the observatories. You know, the big observatories that we watch stars with. Well, they have to, if they want to take a picture of a star, that's a problem, because if you just set your camera up, when you got your picture developed, it'd be a straight white line. Because what? The Earth rotates, and you don't follow the star with the camera. Well, that's what the observatory does. And so they have to have a clock driving this thing that's really, really accurate. Those kinds of clocks are still out there. You can still buy them if you have a lot of money, because they're antiques these days. But they would hold maybe 2 or 3 years in 1 second. 1 second in that length of time. And that was very, very good. Well, finally we needed to get to some way of having what was called side real time. Let me turn this so you can see it. Because this is on your sheets you have these vocabulary words, and I want to add one to it. You have those vocabulary words that start with, it's at the top of your sheets that are stapled, and the first word is movement. Well, I want to add one. I want to add this word, side real time. Because somewhere, somehow, there must be some kind of timing going on that is going to be perfect all the time. That we can say, oh, okay, it's perfect. I can set my clock to that. The tower clock that was in the Portage County courthouse with its strike on the hour, every hour, ran about 1 second a month. Pretty good. There's a lot of reasons why it was so good. But people would, that was a wonderful thing. People would hear that and set their clocks and their watches to it. That's side real time. And what else did we used to do? Well, we did things like our side real time was also through the years, hey buddy, you got the time? On the street. You know, somebody would say, hey, you got the time? Like that. Why? Because where was side real time anyway? You know, and how about, I told you about the tower clock here in Ravenna. Bank clocks. People would look at bank clocks. Banks are trustworthy places, right? So they ought to have good time. Our radios. Remember getting the time on the radio? And sometimes they'd say that it was Greenwich time. And you'd have those little boop, 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 boop. The time now is exactly, and they would say it. And then an hour later, they do the same thing. And that's how we got our time. On our telephones, we used to be able to call a number and get the exact time. TV would do it, and, you know, people didn't know, but those times were always 2 minutes off one way or the other. They really weren't good sidereal time. And today, we have our iPhones, and I don't know where mine is. It's in my pocket. We have our iPhones today. For a certain reason, they keep very good time. So we have this sidereal time. So what is it? It's a standard of time keeping against, timekeeping against which a timepiece is set. It's the last word. Well, what did they do back when we didn't have any of this good timekeeping going on? What did they do? Well, in Greenwich, they used a telescope. Get this back so you can see it. Here's the Earth. The Earth is a clock. Okay? Now, who knows the answer? How many hours in a day?
24.
How many agree with him? 24.
I agree.
She agrees. How many don't agree with him? Because you know I'm going to trick you. Right. Well, you're wrong. There's not 24. There is pretty exactly 23 hours, 56 minutes, 4.1 seconds in a day. And so, we do this, you know, we lose time. We lose, you know, some minutes every day in our daily keeping of 24 hours. Well, that works out not too good at the end of a length of time. Our calendars suddenly become wrong by 1 day or so, and that happens every 4 years. So we do a trick. We say, okay, every 4 years, we're going to add a day to that year. Instead of 365, we have 366, and that fixes it. Okay. It's not really fixed, by the way. You might explore this. Look up Gregory the Fifth, Pope Gregory the Fifth of the 15th century, for 1500s. He knew that that wasn't going to be right every 4 years, so they changed the formula. Every time we have a century year now, if it is divisible by 400, it will be indeed a leap year. That was the year 2000, divisible by 400. But the year 2100 is not divisible by 400, and it will not be a leap year, even though it's divisible by 4. Same thing is going to be true for the 22nd century and the 23rd century. They're going to be the same way with the 24th works. They set up that new rule so that we could be closer to within 15,000 years. Fun. Okay. The Earth goes at a certain speed. At the equator, it's rotating at 1,000 miles per hour. That's pretty fast. We're doing about 600 right now, toward the east. Okay. So the Earth then, if we know the details about it, we can make it be a clock. And indeed, that's our sidereal time. How did they make that happen? Well, we've got these lines on the globe, and the ones that go from the North Pole to the South Pole, we call those we call them meridians. They have them numbered. The prime meridian goes through Greenwich. It's 0. On the other side of the Earth, it's 180 degrees. It's called the anti-meridian. And in Greenwich, they have a slab of concrete, and they have a marker in it, and the prime meridian goes right through that marker. And they set this telescope up right over top of that marker. And they have a plumb bob come down and they got it right on. And they focus the telescope on what they call the clock stars. This is what they used to do, get this exact time, this sidereal time. They call them clock stars. The stars were supposed to be very accurate. Well, inside the telescope was a crosshairs. It was like this. So it had a little space in the middle, like that. And so as they focused on the star would come along and go inside this space and then back out, and that'd be 1 second. And that's how they did it. That's how they had a sidereal time. It wasn't accurate, by the way. And when we got into other things, we discovered that the accuracy we needed was greater, because we began to play out in space with rockets and stuff, try to land stuff on Mars just right and so forth. We had to have very good timing, much better than that. All right, so this whole thing here wasn't good for space age, but this got closer. Around 1950, okay, here we were doing 2 seconds or 1 second every 2 years or so. Best we could do. But here, they discovered that a quartz crystal, like in the old radio days, we had capacitors. Who knows what a capacitor is? Anybody? You do? Okay. A capacitor is a piece of equipment inside of a circuit that when you put a power on it, it lets that power come in, but then it spits it back out in a certain length of time. It just does it like that. That's what a quartz crystal does, interestingly. They can put a power on it and make them different sizes, and when the power came back out of it, they can make it be 1 second. Very close. They got down to 1 second in a year. In a year. And that was great. The better they made the quartz crystals, the better they worked. And so they tried that. But now today, we don't do that. We do have quartz watches. I've got one. There's one, there's this guy over here. But actually, there's that one right there, number 17. It's called an atomic clock. It's really a quartz clock with a special piece of equipment in it. That's what it is. So these atomic clocks, you think you're getting a really fancy, you pay, I don't know, 30, 40, 50 bucks for that thing. It's just a quartz movement, but it has one special feature, which I'm going to tell you about. Okay, they discovered that if they took a lithium atom, or now some other kinds of atoms of elements, and put the power on it, it will indeed keep time very well, within thousands of years, 1 second. Okay, in Boulder, Colorado, there's a computer, and in 11 other places around the world, there's a computer, 12 computers. They have lithium or some other kind of atom in them that they do that to. All these computers, all 12 of them, are netted together. They take, every second they do this, the computers take their 12 readings and divide it by 12 and take an average. And they say, okay, that's the time. They send it to the GPS satellite, and our iPhones read it. And so your iPhone is the very best timer you could ever have. It's really good. And so you can set all your clocks and watches by it. All right, now I've got one of these watches that's supposed to work like that clock does. What's it doing? Well, in Boulder, Colorado, they send out every so often a radio signal. It's a radio signal. It's not a wire. And these clocks in my watch pick up that radio signal and adjusts its quartz movement So what you have in one of those kind of watches and that clock is a quartz movement that gets adjusted every so often by a radio signal. Okay. Now, display. We have three kinds of displays. Originally, with clock or timekeeping, it was audio, or it was audible. It was a bell, or somebody yelled or something, and that's how they did it. Somebody was sitting with hourglasses and watching it, or maybe a sundial, and the monks would be out in the field working, and a brother would be back in the monastery, and he was the timekeeper. And when it was time to come in and eat, at a certain time, he'd go out and hit the bell. And so that was timekeeping. However, we like other ways to be told about the time besides the bell ringing. These guys do that both. They do it with the face, and they do it with a chime and a strike. Okay. So we have analog. That means hands. An analog clock has hands. Digital. Interestingly, right here, with this kind of regulation, we had these wonderful bedside clocks. I'll bet you guys have had them. That they light up, you plug them into your wall behind your bed, and they have these little rollers inside that are digital. And the clock movement would roll those around and show you the time, you know. So that was digital. It's just not the digital that we think about now, today. All right. So those are the way that the clock talks to us. So what do we have to have? We have to have power, we have to have some kind of regulation, and we have to have the clock talking to us. Okay. Okay. I told you about the globe and how it does this wonderful thing for us. Here's this beautiful clock. It's been it's a Seth Thomas. I did this clock. I didn't refinish it. I didn't do any of that. I don't own it. It's a customer's clock. They're not here tonight, but this clock has two movements in it. It was made in the latter part of the 1800s on into the 20th century, on into the 1900s. That's when it was made, by Seth Thomas. Okay, up here is a regular clock movement. You wind it up, it has a pendulum in it, and that's how it keeps time. Okay, but down at the bottom, it has this unbelievable mechanism for its day. No batteries, no electricity, nothing like that, and you don't wind it up. And it doesn't run by weights. Here's what happens. In a way, it runs by weights. On the back of the clock movement is this cam that has a step in it. And while this clock runs, this cam turns, and touching the edge of the cam is a wheel. And as the cam climbs in its heights, the wheel runs along and it lifts up this little weight. Lifts it up. And when it gets to midnight, it drops off the edge of this little notch. The weight goes boom, down in. And this calendar moves one day. You say, well, that's kind of cool. But this calendar even does more. At the end of the month, it knows it's the end of the month. And if it's a 30-day month, it will jump over the 31 and go to the 1st. It'll also move the other little dial to the day of the week. But what about February? Well, on February 28th, on a 365-day year, it will jump over 29 and 30 and 31 and go to 1. But what about the 30-day months? Well, on the 30-day months, it will jump over the 31 and go to the 1. But what about every 4 years? Yes, it doesn't. If you can keep it running and keep it wound, it will know when the year should be 29 days and not 20 days. This was built 1900. The maker of the two movements is a man named Nix. He made one kind, another guy named Andrews. Now, I've done this clock, and I want to tell you, it's a bugger. I've got a book on it, an old book, that explains how the movement works. And I had to study it and study it and study it to get it in my head so I would know how that should work, to set that little part. Well, then you gotta test it, you gotta run it through all that stuff in order to get it. Yeah, all right. All the clocks are going here. Okay. What the clockmaker fixes. All right. Well, before we do that, we're going to look at 2 videos. First, we need to do this one. Let's do this one, Tom. Let's run this one. Okay, so what this clock is, it has both a strike and a timekeeping set of wheels. And I this is in my shop being fixed to go back to an owner. I fixed the time side right here. It has bushings in it. Bushings are what you put in the holes to make them back being round instead of slotted again. And you do it with drills and so forth. If you're interested, I've got the tooling up here, you can look at it. This side is the strike side. It's worn out too, but I didn't fix it. I just cleaned it and put it back in. So you can do this, you can take this thing and go like this, and you can see them wobbling around in their holes, and that's the problem. On this side, you can do that, and they don't wobble, because they're fixed. Tom took a video of it. Jans is the name of the manufacturer. It's a German, it's about 120 years old. There's the back of the movement. Look at the worn out one. Look at the one that's fixed. See the difference? Okay, we're going to pass this around. You can do it yourself. You can just go with that one and do that with this one. Okay, now we're going to watch a video here. What it is a video of the clock in the tower that was in the old courthouse. It's a Seth Thomas number 18. You got the sheet on it. It gives you the specs on it. But we're going to watch a video that Tom made about it. It's kind of fun to watch.
Are you watching the time?
I am. It's 3:03. Are you watching time?
Just so you are.
I don't know if we have any time to look at.
Before the 1880 Portage County Courthouse was built, the county fathers pondered their options for enlivening the public square in Ravenna. When they considered a clock tower, a local jeweler opened his Seth Thomas clock catalog and showed them this. This clock could drive 4 sets of hands and strike a large bell. So even though it was 6 feet tall, required a 14-foot pendulum, and weighed 3,300 pounds, they decided to buy it.
This is the weight-driven clock.
After the courthouse was raised in 1960, The clock was eventually moved to the Portage County Historical Society and placed in a newly built clock tower.
Listen to it tick.
Resistance of the air.
Do you hear it?
Yeah. It ain't air cool. Because of-
It's 2 seconds.
2-second pendulum. Is that it?
You're gonna say something
Oh,
profound.
let's go.
You're gonna say something.
All right. We have more on the pendulum here, friends. 2 seconds.
And then this one.
The pendulum is 14 and a half feet long. As you can see from your sheet, how much does it weigh? Did it say that?
25 pounds?
Yeah. It is so heavy and so long that the moon phases, the moon affects it. You gotta set it up just right so that.
Now we're on the first platform. Looking at the horizontal here on the left, you can see it slightly turning. As it does, it moves the hands on the four clock faces that are on the second platform. The cable that you see going down into the drum stretches above and across the clock via a pulley system to the huge weights that actually power the clock. Those weights have to be pulled back up once every 8 days.
Right there. See it with
Even though it weighs 400 pounds, the weights, you can take your
Here,
little
we
finger,
are looking at the
put it in that
pendulum
little, see
again,
that?
as it is being
As
pushed
much.
back and forth.
You can put your little finger right in there.
Rollers every
And it won't
2
hurt.
seconds.
Confusing,
Just
huh?
to the left of the
No, I can build
pendulum
a clock,
and
so I
below,
have an idea
you
what
see
it's
the
going.
hour locator hand of the clock faces. This allows the operator to
Did
set
wiggle
the
like that?
time on the clock
That's
faces
what- see it wiggle?
from the inside.
4 out.
To the right
This
of the
side don't
pendulum is a chain that attaches to the electric motor that winds the clock.
Keep going.
Okay, this pendulum rod is interesting. This clock was made in
It's shafted.
1870. So you think they were smarter or dumber than us?
You wiggle your finger out, wiggle it up and down. You understand.
Well, because its pendulum is so long, 14 and a half
You
feet,
get out there.
it does have a center of gravity, just like this pendulum has a center of gravity. Somewhere in this length is where the gravity is centered for this clock. And so that's what you adjust when you move that wheel. Well, when you take a 14 and a half foot length and make it weigh 300, was it 25, 50 pounds? The temperature affects that tremendously. And so there the thing sits in that tower at 0 degrees, at 100 degrees. You know what's gonna happen. That thing's gonna get longer and go slower, get shorter and go faster. 1870, they made that pendulum rod be 3 pieces. Zinc and 2 parts of it are steel. And they are made in such a way that the zinc expansion and contraction counteracts the steel expansion and contraction exactly the same and holds the gravity, center of gravity on that pendulum right on. And so they could run that thing and only have to adjust it for 1 second a month. 1870. All right, a wonderful piece. They couldn't have made a better purchase in that day than do that with that clock. People are going to set their clocks and watches by it, and it's going to be a great thing. Well, in 1960, they tore it down. And the clock almost died. In the 11th hour, we say, a guy by the name of Charles Wass came along with his truck, and they were ready to slam the ball into that tower. They'd already taken the roof off. And he said, I want the clock, I want the clock. And well, they hoisted him up there, and he had another guy with him. They unbolted it, hooked the crane on it, lifted it up, put it in his truck. He took it home on Meridian Street, put it up in the attic of his house, cut a hole through the floor of the attic into the ceiling of the bedroom below and ran that clock for 10 years. Saved it, literally. Well, the Historic Society came along and they decided to make a tower using some of the old bricks from the original courthouse, which they did. And they got the clock from Mr. Wask and they installed it in the tower of that right there. Don't move it yet, Tom. What you see is what I will do when I fix the clock. When I fix the clock, the first thing I do is take the hands off. Why? Well, you gotta take the movement out of the box and you have to take the hands off because the hands won't fit through the little hole. So, we're gonna fix this clock. We've taken it apart, and that's what you're gonna see here, how we took it apart a little bit. Right there, we're up on a big hoist from my son Andrew. He's got the tree business, and he's got these pieces of equipment. We're taking the hands off one of the faces. They're about this long, a minute hand, made out of wood. And so we took the hands off, and away we go. Okay, there's one Mr. Tristan up there, and we're getting ready to undo the parts of this clock and lower it down through the tower by chain hoist in order to get it. We have to take it apart now in pieces to do this.
Where the clock right now is right here, right?
Yeah. Yeah.
Yeah, okay. Such good looking guys.
Okay, Tristan's, below him is open space down to the floor of the tower. And here comes some parts of it. There's the table sitting on the floor. It's as you can see in your picture, it's a big table that all the wheels fit into. They have it sitting on the floor. We get it outside, and we have to look at the snow we were fighting that day. We had to load it up on a trailer of Andy's, and we took it to Andy's business on Cleveland Road, 822, which is the old AT&T building. And Andy has his storage in there for his tree equipment. Besides that, he rents space to RV people and boat people to store. But he has a workshop in there that's really nice. And he has invited me to move my shop from my house to his place. So we've gotten all the Seth Thomas parts there. Now we're gonna start to fix it. It's a beautiful thing. It is. It doesn't show you in this picture that you guys got, but there's all this, there's 2 tones of green it's painted with, along with black. And then on the legs and the sides and other places of the clock, it's got, what do they call it when they do? Pinstriping. All kinds of pinstriping on this thing. And it sits up in a tower for 70 to 90 years in the pigeon poop and the mice and the cobwebs and the dirt and all that. There, it's just beautiful thing. It's kind of like a fire engine. You know how it's beautiful all over, inside and out all the time? Well, that's how this was. And that's what we're gonna do. That's our plan. It's gonna take us over a year, for sure. We need some money. Talk to your friends.
Okay,
Okay,
thank you very much.
now, you can, as I say, take pictures and hang around a little bit. Well, I'm gonna be here to 3:40. Can answer questions if you want. You can look at some of this stuff up here that I use to fix clocks. And there you are. Thanks.
On the wind-up clock, you have to move